Hi guys, welcome to lesson 6.3. In 6.3 we're going to be talking about performing some operations with various functions. So we've been talking about polynomial functions and square root functions and all kinds of various functions throughout the course of Algebra 2A, and now we're going to talk a little bit more about what we can do with those functions. And sometimes when we have like functions being kind of married together, and so that's going to kind of get into this idea of operations on functions. So we're going to get into some of that stuff, but just a couple definitions to get us started. First of all, a power function is basically any function that has y equals ax to the b power. An example would be like y equals 3x to the fourth, for example. And now again, that can be a rational, b can be a rational number, so maybe it's 3x to the 4/5, for example. That would be an example of a power function. Again, anything that has x being raised to a power, it may or may not have a coefficient here. It could just be a 1 if we wanted to, but basically any function involving x with a power is a power function. Okay? Now, the composition of a function g with a function f is called h of x, and again, that's just the result of marrying the functions together. And this is g of f of x, and basically what we're saying here is we're saying we want to embed the function f within the function g. And we'll get some practice of that when we start talking about compositions on the next page. Now, the part that I think about this is really confusing is this idea of the domain. Remember, the domain is the possible inputs for a function. And so the domain of the function h, the domain of the composition, is the set of all x values such that x is in the domain of f and f of x is in the domain of g. Now, without practically getting into some actual examples of this, this is really hard to explain. But probably the best way to talk about this in terms that might make sense is we can say, look, if x is not okay in the first function, then the same x is off limits for the second. Now, this is absolutely no mathematical terms to that, but basically we're saying, look, if you can't use this value of x in the first function, then you can't even consider that possible x for the second function when we start looking at the compositions of those. So again, that looks a little bit sketchy, but make sure you write that down and kind of get it and maybe let that sink in a little bit, and as we start working through the next piece of this, it may or may not make a little bit more sense. All right? So let's talk a little bit about operations on functions. First of all, on operations of these functions, we want to say let f and g be any two functions. A new function h can be defined by performing any of the four basic operations, the four basic operations being addition, subtraction, multiplication, and division. All right, so we can take two functions and add them together. For example, if f of x is the function 3x and g of x is the function x plus 3, then we can take whatever f of x is and add it to g of x. So here we have f of x, which is right here, and g of x is this function here. And when we add those two functions together, all together, what do we get here? This is then, we just combine like terms, which is 4x plus 3. All right, we can subtract those functions. So once again, this is my f of x function, which is right here. This is my f of x, and my g of x is this function right here. And we can subtract those. Now you got to be careful here, because remember, when we subtract something, we have to subtract both of them. So really, this is plus a negative x and a negative 3. So this becomes 3x minus an x, which is 2x, and then minus 3. All right, we can multiply polynomial functions. This is 3x times x plus 3, because this is what f of x is, and we're multiplying it by the function g of x, which means we have to distribute, which becomes 3x squared plus 3x. All right, and then finally we can divide those two functions, f of x divided by g of x. Well, that simply becomes 3x over x plus 3. All right, and we really can't simplify that at all. Now, this is kind of a little tricky, and we should kind of pay attention to this here. It says the domain of this function h, and just in all of these, the domain of the function h, which is the result of adding, subtracting, multiplying, or dividing, the domain of that function consists of all the x values that are in the domains of both the functions f and g. So we're going to refer to a function as just an f and a g. All right. Additionally, the domain of the quotient, so basically just for this last one, we have to restrict the domain because while we can say, look, what is g of, x? Well, that's the function x plus 3. So if I did g of 1, that would be 1 plus 3. That would be g of 2, which would be 2 plus 3. And we can get various values for that. In this particular case, though, because we cannot divide by 0, like dividing by 0 would not be a good thing here. So that says that if x was equal to negative 3, if x was equal to negative 3 in this very last one, that would cause a problem. X equals negative 3 doesn't cause a problem in any of these except for the very last one. And the reason for that is because if x were equal to negative 3, then f of negative 3, sorry, not f of negative 3, g of negative 3 would be equal to negative 3 plus 3, which is 0. And so if if x equals negative 3, then I would get 0 on the bottom of this fraction, which, as you know, we can't divide by 0. So it says the domain of the quotient does not include x values for which g of x is equal to 0. And as we said, that value here would be when x equals negative 3. All right? And so we're going to say that negative 3 is off limits. And that kind of goes back to what we were talking about. If you know, g of x is okay. I mean, by itself, g of negative 3 is 0. By itself, that's okay. But when it's in the denominator of that fraction, unfortunately, we can't have a 0 in the bottom. So we would say that negative 3 is off limits. So it would be any number except for negative 3. All right, so let's do a couple examples. Let's add some functions together. First of all, let's do f of x plus g of x. Now, f of x is this and g of x is this. These are both power functions. In this case, since they have the same variable and the same exponent, all right, this basically just says we have three of these plus negative 5 of these. So 3 minus 5, x to the 1/2 powers. Now, again, this could be x to the 3rd, this could be x to the 8th, this could be x to the 1/2. It doesn't matter. Because they have the same variable part with the same exponent, this simply becomes negative 2 x to the 1/2 power. All right. In f of x minus g of x, this becomes 3x to the 1/2 minus a minus, 5x to the 1/2. And as we know, minusing a minus turns into plus. So this is simply 8x to the 1/2 power. Now again, don't be intimidated by that half power. Doesn't really mean anything besides the fact that because these match exactly, we can go ahead and combine the coefficients. Now, it says find the domains of f plus g and f minus g. Well, in the domain of f of x, we can't have negative numbers. Okay, we cannot use negative numbers. Because you can't take the, again, if this was to the 1/2 power, this is 3 to the 1/2 power, take a value of x. Remember, the 1/2 power is the same thing as the square root, so this says 3 times the square root of some number x. Well, if x is negative, if x is less than 0, that means that we would only be able to take the square root of positive numbers if we're going to only deal with real numbers, okay? So if we're including imaginary numbers, then absolutely, you could use negative values for x. But because you cannot take the square root of a negative number in the set of real numbers, it says the function of f and g both have the same domain, which is all non-negative numbers. Or all negative values. So the domains of f plus g and f minus g must also consist of the same values, all non-negative values, or numbers, or however you want to say that. You can't have negative values of x in either f or g because you can't take the square root of a negative number, and so therefore the domains are restricted to those same values of x. If you can't evaluate this for a negative value of x, then you're not going to be able to evaluate the sum. And that kind of gets back to that thing that we said before. If x isn't okay for this one, then x isn't going to be okay for the sum of the two functions. And so you can't use negative numbers for that. Let's try one with multiply and divide. Our function here is 7x, and g of x is x to the 1/6 power. So first of all, let's see what the product of these two are. So again, the product is 7x times x to the 1/6. Same basis here. Okay, forget about the 7 for just a second. That's out in front. What's x to the 1 power times x to the 1/6? Well, we said before we would add those exponents. Now we're not going to make this x to the 1 1/6 power. That doesn't work for us, all right? So instead what we're going to do is we're going to think of x to the 1st as x to the 6/6 power. Now 6/6 plus 1/6 becomes x to the 7/6. All right, and so then we would be, we'd get that function x to the 7x to the 7/6 power. All right, what about the quotient of those? This becomes 7x over x to the 1/6 power. All right, and now because this is the quotient of powers, we have x to the first over x to the 1/6. Well, x to the first is the same thing as x to the 6/6. And so now, because they have the same base, we'd subtract the exponents. This becomes x to the positive 5/6 power. And we still have the 7, so x to the positive 5/6 power. All right? Now, here's where we get a little bit tricky. Keep in mind that for the first function, f of x, x can be anything. X can be positive. It can be negative. You can multiply any number by 7. No big deal. But g of x is restricted such that x can only be in the, x must be greater than or equal to 0. All right? Because you cannot take the 6th root of a negative number. Okay, that's no good. So since you can't take the even root of a negative number, which we talked about in the previous lesson, the domain of x consists of all real numbers. Okay, you can multiply anything by 7. However, the domain of g only consists of all non-negative numbers. Now, I know what you're thinking. You're going to say, well, why can't you just say all positive numbers? I mean, that seems to be a lot easier to say than all non-negatives, right? But you can't just say positive numbers, because positive numbers are all the numbers. Here's my number line, right? Here's 0. Here's all the positives. Here's all the negatives, all right? We can't use these negative numbers over here, but I certainly can take 0 to the 1/6 power. It's just 0. All right, so by saying all non-negative numbers, basically I'm saying include 0 and all the positives. So you could say all the positives plus the number 0 if you wanted to, but now, again, you might just as well say all non-negative numbers. So, all right, so the domain of f times g, again, if g of x, we can't even consider these numbers over here, then the product and the quotient can't consider those numbers over there either. So because the domain of f times g is then going to consist of all non-negative numbers, because the function g restricts those values, we can't even use those for g, so the product of them won't consider that either. All right? Now, the other one that you have to consider is this, and like we talked about, g, the function g was x to the 1/6 power, so g of 0 is simply 0 to the 1/6, which is 0. And that would pose a problem right there, because now I would get 0 to the 1/6 power. All right? And so 0 to the 1/6 is 0, and so that's no good. Now, you might look at this and say, but wait a minute, 0's okay here. Who cares, right? 0 to the 5/6 power. But because we're dividing those two functions, and x to the 1/6 power when x equals 0 is going to make this fraction undefined, because you're going to get something over 0, which, again, is undefined. So because that x to the 1/6 is in the denominator of that fraction, x can't be equal to 0 either. So because g of 0 is equal to 0, the domain of f of x is restricted to all positives. Now we can say all non-negatives, plus we can't use 0 either. So basically now we're just going to say all positive numbers. So we have to leave 0 out, because 0 would cause a problem here. All right? So hopefully that makes sense to you guys. I believe now we are on a checkpoint problem. And so why don't you go ahead and try this checkpoint example, and we'll be right back with a solution. All right, so there are 5 things we have to do here. So our functions are 5x to the 3/2 and negative 2x to the 3/2. We need to find the sum of them. Okay, well that's 5x to the 3/2 plus negative 2x to the 3/2. And basically you have 5 of them and negative 2 of them, so that becomes 3x to the 3/2 power. No big deal, right? Part B. Part B then says we want to find what is f minus g. And so f minus g would be 5x to the 3/2 minus a negative 2x to the 3/2. And so minus a minus turns into a big old fat plus, and this becomes 7x to the 3/2 power. All right? Now, part C gets a little trickier. Now we have 5x to the 3/2 times negative 2x to the 3/2. And so when I multiply 5 times negative 2, I get negative 10. And x to the 3/2 times x to the 3/2 becomes x to the 6/2, because again, x to the 3/2 times x to the 3/2 says we would add those exponents. So that's x to the 3/2, x to the 6/2 But then again, what's x to the 6 halves? Well, that's x to the 3rd, right? And so we're going to go back and we're going to clean this up a little bit. We're going to get rid of that 6 halves because 6 divided by 2 is simply 3. Now, you might be looking at that and saying you can raise any number to the 3rd power, so what's the big deal? But we're going to actually have to restrict the domain here, so we'll get to that in just a second. Part D asks us to take the quotient. This is 5x to the 3 halves over negative 2x to the 3 halves. Okay, well, this becomes x to the 3 halves over x to the 3 halves, which becomes x to the 3 halves take away 3 halves, which is x to the 0, or simply 1. So this becomes negative 5 halves. This isn't much of a function because it doesn't even have an x in it, but that's okay. It's still the result of dividing those two polynomials. Now I'm going to do part E over here in the margin. It says find the domains of them. All right. Now in part A, if I look at, I first have to consider the possible values that I can use for x in both f and g. All right. So for f, x has to be greater than or equal to 0. All right, I can only use the numbers that are non-negative. So what they said in the book is they use non-negative. I'm going to use the same idea here, but basically to say non-negative, I'm going to say x is greater than or equal to 0, saying all the numbers that are 0 or bigger. All right, same thing for g. All right, so x has to be greater than or equal to 0. Because again, they have to be positive because this rational exponent of 3 over 2 says effectively this is 5x times the square root of, sorry, that's not 5x. It is 5 times the square root of x because it's second root and then raised to the 3rd power. And I cannot take the square root of a negative number. All right? So I can't use negative numbers. I can use 0 because the square root of 0 is 0. And then you cube it and you're in good shape, right? All right, so f plus g, the domain for f plus g is going to be the same, right? Because this isn't going to cause any issues. Basically, x has to be positive or 0. All right, so we're going to say it's all the non-negatives. And so, again, I'll use x is greater than or equal to 0. All right, for f minus g, same thing. X has to be greater than or equal to 0. All right, for f times g, that's also x has to be greater than or equal to 0. Because, again, negative numbers are off limits for their product. Even though you can take any number, whether it's positive or negative, to the 3rd power, that doesn't matter. But because negative numbers are not defined back up here, we can't even consider those values for the product. All right, so we're going to leave out those numbers when we start constructing our domain. Now the last one is, again, a little tricky. For the quotient, because, again, for quotients, you always have to be concerned with zeros in the denominator. That cannot be equal to 0, because if it is, the whole thing is undefined. So for the domain for f over g, now what we're doing is we're going to say two things. Number one, it has to be greater than or equal to 0, but because negative 2 times 0 to the 3 halves power is going to lead to a big old fat 0 here, that would make the whole thing undefined, right? So now we're simply going to say that for f over g, the domain has to be strictly greater than 0. So you could also say for all of these, that same thing. This is all sorry, my hand's in the way. This is all non-negative. And this is all positive. So you can write out all non-negative numbers for f plus g, f minus g, and f times g. And then f over g is simply all positive values of x. All right? Okay, so let's talk a little bit about compositions of functions. Compositions of functions says a composition of a function g with the function f is some function h of x, very similar to how we defined it before, such that this is now g of f of x. All right? So what I call this is I kind of talk about compositions, and what we used to call this is we used to call this embedding. So we call it an embedded function, because really what you're doing is you're embedding one function into the other. All right? Now, where we get a little tricky here, and this is the same graphic that's kind of helpful from before, if the domain of f, again, those are the values of the inputs that I can plug in, is going to lead to a set of function values. All right? And that set of function values, again, we have to be very specific because the inputs of g might be these numbers down here, it might be all of these numbers. All right? But just those outputs of f then are put into the function g, and then we get this function g of f of x. All right? So maybe the Venn diagram is not helpful. It's the same idea, though. If we can't consider those values of x for inputs of f, then we can't even consider those values for g, even though those values of x might be okay for g. So the domain of h is the set of all x values such that x is in the domain of f, and f of x is in the domain of g. All right? Again, very confusing in that wording, but let's kind of get into some examples, and like I said, hopefully this will make a little bit more sense to you. So we want f of g of x. What we're going to say then is, if I asked you for what is f of 3, you would tell me that's 6 times 3 to the negative 1 power. If I asked you for f of negative 9, that would be 6 times negative 9 to the negative 1 power. If I asked you for f of apples, this would be 6 times apples to the negative 1 power. All right? So all I want to do is I want to say, what is f of g of x? So in place of g of x, I'm going to plug in, I'm going to embed the function g of x. All right? So now I want f of g of x. And so I'm going to replace g of x with what g of x is. And now the function f says take whatever's in here, 3, negative 9, apples, whatever it is, and I'm going to do 6 times whatever this is, which happens to be 3x plus 5, and raise it to the negative 1 power. All right? Now, unfortunately for us, this doesn't simplify very well, and so we can just take this one step further. Remember, anything to the negative 1 power simply becomes 6 over 3x plus 5, and we can't simplify that at all. We'll come back to domains in just a second here. All right? G of f of x says, all right, take the function g, and if I asked you for what is g of 10, you would tell me that that's 3 times 10 plus 5. If I asked you for g of negative 9, you would do 3 times negative 9 plus 5. I don't have to do apples again, do I? 3 times apples plus 5 would be g of apples. Well, now we're taking g of f of x. So I'm going to say, what is g of f of x? And I'm going to take the function f, and I'm going to embed that here, because now I'm taking g of the function f. Now, g of x before used to say take 3 times whatever's in these parentheses and add 5. Well, whatever's in these parentheses, whether it's 10, negative 9, or apples, you're going to get x, 6x to the negative 1 power. Now we have to simplify this. This is 3 times 6 times x to the negative 1, which becomes 18x to the negative 1 plus 5. All right? Now what about f of x? That's kind of tricky. Now we're saying, well, again, we're going to bury f of x within that set of parentheses, and f of x says it's 6x to the negative 1 power. And so the function f says take 6 times whatever's in the parentheses, which is 6x to the negative 1, and raise it to the negative 1 power. Now again, I realize that that's kind of tricky here, and perhaps I should have used some different colored pencils, but we're just taking, for the function f, we're taking 6 times whatever's in the parentheses and raising it to the negative 1. All right, so this becomes 6 times, and then 6 to the negative 1 becomes 6 to the negative 1, and then this is x to the negative 1 raised to the negative 1 power. Well, remember, power of a power says to multiply, and negative 1 times negative 1 becomes just 1. Now, 6 to the first times 6 to the negative 1 says add these exponents, and we get 6 to the 0 power, which is just 1. So all of this worked out, we get simply x. Now, that doesn't always happen, but in this case it does. All right. Now, we have to consider the domains of f of x and g of x. Going back to the original function f, we need to kind of take a look at these domains. So I'm going to clean off this margin a little bit, and we're going to put our answers over here instead. And we'll talk a little bit about the values of the function, and we'll fill in the blanks, okay? All right, first of all, when we're talking about the domain of f, for f of x, the values of x that we can put in there have to be greater than or equal to, actually, I'm sorry, they can be anything. You can put a negative number, because again, x to the negative 1 basically says this is 6 over x to the first. So basically, as long as x is not equal to 0, so I can say x is not equal to 0, or I can say all non-zero numbers. So the function f is defined for anything that's not 0. All right? The function g, well, that's defined for anything. X can be any real number, because you can take anything and multiply it by 3 and add 5. All right? So those are the domains of f and g. All right? So because we can't consider 0 for the function f, then we're going to have, when we take g of f of x and f of g of x, we're going to have to leave that value out, because 0 just doesn't work. So it says the domain of f of g of x, all right, the domain of f of g of x consists of all real numbers, except for x equals 0, because x equals 0 is going to cause a little bit of a problem. All right. Now the other value that we have to be concerned with here, I'm sorry, that's not 0. That's not the one they're looking for here. I'm going to say all real numbers except 0. Okay? And again, I have to consider, I can't put 0 in here because for f of x, 0 would lead to an issue here. All right? So all real numbers except for 0. And then we also have to leave out the value of 5/3. Okay? I'm sorry, negative 5/3. All right? And the reason for that is because g of negative 5/3 would give me a 0. If I put negative 5/3 in here for x, this is 3 times negative 5/3, which is negative 5, and negative 5 plus 5 is 0. So I would have a 0 on the bottom of this thing, which would lead to something that's undefined. So I can't use 0, and I can't use negative 5/3. Outside of that, all numbers are okay. All right? And so, again, this says x can't be equal to negative 5/3 because negative 5/3 is equal to 0, and that is not in the domain of f. All right? So that would lead to an issue. All right? Again, it says, notice that f of 0 is equal to 6/0, which would cause a bit of an issue, and that's kind of what we talked about before, which would be undefined. All right, so let's go ahead and take a look at the next one. It says, what about the domains of g of f of x? Well, first of all, g of f of x, if you look at the result here, this would be 18x to the negative 1, which again says that x can't be equal to 0, because again, 18 times 0 to the negative 1 power basically says 18/0, which would lead to an issue, right? So again, it would consist of all real numbers except for 0, because again, 0 is not in the domain, because 0 is not in the domain of f. So once again, if I put 0 into the function f, that leads to a problem. So I can't consider 0 at any point when I'm trying to consider the values of f of x. All right? All right. So there is a checkpoint problem down below. Go ahead and try that one. I'm just going to put up the solution for you in just a second here, and then we'll talk about your concerns when we see each other again. All right, so for f of x, and it might not be a bad idea to consider domain from the very beginning. For f of x can be any real number, right? And why is that? Okay, any real number, because you can multiply any number by 5 and subtract 4. So f of x, there are no restrictions. For g of x cannot be equal to 0, because if x is equal to 0 here, you get g of 0, which is 3 times 0 to the negative 1, which is 3/0 to the first power. And again, 0 to the first power leads to an undefined solution. All right? So we can't consider x equals 0 for any of these compositions with the exception of letter C, because 0 is not defined for the function g. So again, if it doesn't work for one of them, it can't work for either of them. So we have to leave out, if we're doing a composition involving f and g, we have to leave out the values of x equals 0. All right, so f of g of x, we want first, what is f of g of x? And again, that's f of the function g, and in this case, the function g is 3x to the negative 1. Now, the function f says take 5 times whatever's in the parentheses, which in this case happens to be 3x to the negative 1, and then subtract 4. All right, so what you're seeing here is we're saying, look, we've got this right here, and again, my function says 5 times whatever is here. And so again, we're just going to say that's 5 times 3x to the negative 1, and then we're in pretty good shape here, okay? All right. So our next order of business then is to take a look at what happens here. This is 5 times 3, which is 15, x to the negative 1 minus 4. Now, as long as we're talking about domains and ranges, we might as well just put it in here. In this case, x cannot be equal to 0. That's the only value for the domain that would cause an issue, because again, in g of x, you can't have x equal to 0. I see no other issues that would potentially arise from the function f of g of x, and so basically, as long as we say all non-zero, we're okay. So we're kind of addressing part D there as well. How about for part B? Part B asks us to find g of f of x. G of f of x. All right. And so that says take the function g and embed the function 3x plus 5. Well, the function g says take 3 times whatever's in here, all right, which is 3x plus 5, and raise it to the negative 1 power. Well, that becomes 3 over 3x plus 5, because again, the negative power says move it downstairs. Now, there are two values of x that are no good here. Obviously, we cannot consider x can't be equal to 0, because again, it's off limits from here. Also, we would also have to leave out the value of x is equal to... Did I just do that completely wrong? I used the previous value of g of x. Can I change this now? This is supposed to be 5x minus 4. All right? This is 5x minus 4, and this is 5x minus 4. I just had that function g in my head from the previous problem. I apologize for that. Anyway, you've got 3 over 5x minus 4. So once again, x can't be equal to 0. And what's the other value that x can't be? Well, if 5x minus 4 is set equal to 0, and I add 4 to both sides, I get 5x is equal to 4. And so x cannot be equal to 4/5, because if x is equal to 4/5, this becomes negative. This becomes 4, which is minus 4, which is 0. So we can't consider x equals 0, and we cannot consider x equals negative 4/5. Outside of those two values, any other value of x is fine. All right. What about part C? For part C, it asks us for f of x, which basically says take the function f and bury in it the function f of x, which is 5x minus 4. I'll get the right function this time. And so here it says 5 times whatever's in the parentheses, which is 5x minus 4, and then minus 4. Distribute, this is 25x minus 20, and then you still have the minus 4 on the end. When I combine like terms, I get 25x, take away 24. And that's our values for f of x. Now, any restrictions there? No, because f of x can be anything, and since we're not concerning ourselves with function g, we don't have any restrictions to begin with, and it pretty much looks like any number can be multiplied by 25 and subtract 24, and so for that reason, this is all real